In the last class, we were discussing about the amplifiers. As I mentioned, an amplifier has an input impedance and an output impedance. It has some voltage gain and current gain. So let us continue the discussion uh, of yesterday's class. Earlier, I mentioned that at the input port, an amplifier exhibits as some resistance which is denoted by Ri. If I generalize it to an impedance, it becomes now Zi, the impedance at the input port. In general, an amplifier exhibits some impedance rather than a pure resistance at the input terminals, because the amplifiers do involve some capacitances. The capacitances are inherent in the device itself, and some capacitances or capacitors are included in the circuit, similar to the blocking capacitor, that some capacitors are included in the circuit. So because of this reason, it exhibits some impedance at the input terminal. Hence, the it is input impedance Zi, which is defined as VIT divided by the input current IIT. So that is for the input impedance. Similarly, for output impedance, as I mentioned, when the input is short circuited, that means input voltage source is removed and it is shorted, then the output impedance that is appearing across the terminals, output terminals, is the output impedance. And that output impedance can be determined by shorting the inputs and applying an external voltage source V0T. This V0T is now different. It is an external voltage source V0T. And then you will find some input current going into the output terminals, I0T. So V0T divided by I0T is the output impedance. So the I0T is the current which is going into the terminals. So the load current is the current which is going into the load. Therefore, I0T is equal to minus ILT, or ILT is equal to minus I0T. Okay. So when you apply an external voltage source of V0T here, the current that is going inside, when denoted as I0T, so that V0T divided by I0T is Z0. And if it is a real quantity, it becomes R0. And the gain, as we have already mentioned, is V0T divided by VIT under no load conditions, when load resistance is infinity or when the load is not there. So this is the voltage gain of the amplifier, the no load voltage gain of the amplifier. Of course, when you connect the load resistance, it becomes V0T divided by VIT becomes the load resistance, it's the gain of the amplifier under loaded conditions. And with the source voltage included, and with the source included, and when the source is a non-ideal source with some source resistance Rs, then in terms of the output voltage, the gain in terms of the output voltage divided by the sources open circuit voltage, then the gain expression is has some terms, some factor which is equal to Zi by Rs plus Zi on the input side, and another factor RL by RL plus Z0 on the output side, and the overall gain becomes less than the no load gain of the amplifier G. So this is what we have done in the last class. We derived an expression for that. Now, an amplifier also has some current gain. The output current is treated as ILT, the load current. ILT divided by the input current IIT is the current gain of the amplifier, and it is usually denoted by AI, the current gain of the amplifier. Of course, this is valid only when the load resistance is included. So if the load resistance is included, the load current becomes 0. Hence, the current gain is defined as the output current divided by the input current of the amplifier under loaded conditions. Now let us obtain an expression for the current gain in terms of the voltage gain, input impedance, output impedance, and load resistance, and so on. So please note that the output current depends on the output voltage V naught T, and input current depends on input voltage VIT and RI or ZI. Hence, these are all dependent. The ZI, Z naught, voltage gain, and the current gain are dependent on each other. So let us find out an expression for AI in terms of the others. The output current, as you know, AI, the expression for the current gain, which is fixed, is equal to the load current divided by the input current, and the load current is output voltage V naught T divided by RL, and the input current IIT is equal to VIT divided by ZI. Hence, this is equal to V naught T by VIT into ZI by RL, and V naught T by VIT is equal to the gain. Is it gain under no load or gain under load? Gain under loaded condition, because V naught T is the output voltage. V naught T is the output voltage when load is there. If it is not there, this V naught T would be different. So when load is included, that G times VI gets divided between RL and R naught, and that is what is V naught T when load is there. So V naught by RL is equal to IL is under loaded condition, is the expression under loaded condition. Therefore, so this is the gain. V naught T by VIT is the gain when the load is included. That means V naught is G into VI into how much? RL by RL plus R naught, or in general Z naught into ZI by RL. So this is the expression, and therefore divided by VIT. Therefore, it is equal to the gain under no load, so multiplied by ZI by RL plus Z naught, or it is the gain under loaded condition multiplied by ZI by RL. If the gain under loaded condition is given, so then this is multiplied by ZI by RL gives you the current gain, and the same thing is equal to gain under no loaded condition into ZI by RL. Is it clear? Once you know the concept of input impedance, output impedance, current gain, and voltage gain, the problem boils down to simple analysis. The problem of finding the gains boil down to a simple analysis of this type. Any questions? Questions? So normally at low frequencies, are at midband frequencies. I'll explain why midband later. So typically, so Zi tends to be a real quantity, and that is Ri, and Z0 tends to be a real quantity, and that is R0. This is when the transistor is used as an amplifier. Now let us look into an amplifier circuit. We have seen that a self-bias circuit, or maybe a fixed bias circuit. Let me use a fixed bias circuit because it's very simple. Of this type can be used as an amplifier because it biases the transistor in the active region, and we can apply an input signal to it through a coupling capacitor, and we can take the amplified signal from the collector or between the collector and the ground through another coupling capacitor. Now in between, this is an amplifier, and this is the input port, and this is the output port. What we apply here is alternating signals. It may be that it is an alternating signal with mean equal to 0. It means its DC component is 0, but it has an non-zero AC components. It has some AC component with 0 DC component. Then at the output, again, we get amplified version of these signals. That means you will have strong AC component and a DC component is absent in the output. Now, how do we apply these signals to the transistor amplifier, and then how this transistor amplifier can be modeled into the form which we have used? That means this has an Ri at the input side, it has an R0 at the output, it has a no load gain G, and it has a current gain AI when a particular load is included there. So these are the questions now. How do you apply the alternating signals, number one, and number two, how do you obtain the model equivalent of this particular transistor circuit? Because once you know the amplifier model, you know the gains, you know the input impedance, etc. So you know everything about it. Now from the circuit, how to get the model parameters is a question. So now let us discuss about these two things one after another. So let me first talk about RC coupling. Rather, it's a capacitive coupling, and it has an internal resistance over here, where it becomes, therefore it is called an RC coupled amplifier. Now, how does the capacitor couple alternating signals and avoid the DC signals to be coupled? Please note that in this circuit, under active region, the voltage, if it is a silicon transistor, the voltage here is about 0.7 volts. That means this point is at plus 0.7 volts with respect to the ground. And you look at the left side, here the signal is totally alternating. It has 0 DC component. Now this side the DC is 0, and this side the DC is 0.7 volts. Whatever is the alternating signal which we are going to add now, we want to add it to this 0.7 volts. So we want to make this voltage effectively equal to 0.7 plus some small alternating voltage. If this alternating voltage has some variation of about plus or minus 50 microvolts, then this voltage will be changing between changing between 0.65 volts to 0.75 volts. So this is how we want to add this alternating signal to this. So that means the base to emitter potential has a mean value of 0.7 volts. Above that, so the variation is like this. So it may go up to 0.75 here, and it may go up to 0.65 there. So that's what is the base to emitter voltage going to be after adding this alternating signal. So it has a, I repeat, it has a DC component of 0.7 volts, which is the biasing component, plus the alternating component, which is added through this coupling capacitor. Now, if the capacitor is not there, then this voltage source and this voltage gets shorted, and whatever is the current, that base current that is expected to flow through this, will now flow through this side into this source. So to avoid that, we use a capacitor. And as you know, the reactance of the capacitor at 0 frequency is, reactance is, so minus J infinity. So its impedance is minus J infinity, reactance is infinity. Therefore, as far as DC is concerned, no current flows through this. Now for alternating signals, so the impedance is equal to minus J by omega C. If omega C is of the order of a few ohms, please note that this would be only a few ohms as far as alternating signal is concerned. So this alternating signal, which is supplied from the source, is connected to this base to emitter through a small resistance in this fashion. It has a high internal resistance Ri. Now you have VIT here. So now VIT gets divided between this impedance, and this is negligibly small. Therefore, all this voltage is applied across this. Here it is a superposition of this DC component and this AC component. How do you apply superposition theorem? So you use one source at a time with the other source replaced by a short circuit. One source at a time, find that component. First apply one source, find the component, that is 0.7 volts. Then apply this voltage source, find the component with this as short circuited, with this source replaced by a short circuit, and apply how much is applied. So that is directly this voltage itself when this is negligible. Therefore, by superposition principle, the voltage here is equal to this plus this. So that is what equal to this. And since the objective of the coupling capacitor is to block only the DC and to act like almost like a short circuit to the alternating components, the capacitance should be as large as possible. And for audio signals whose frequency range is between a few tenths of hertz onwards, and if it is for telephone quality speech, the frequency band is from about 300 hertz onwards upwards. So the up to 20 kilohertz if it is hi-fi speech, and 3.4 kilohertz if it is telephone quality speech, and that is the frequency components available in the speech. If it is telephone quality speech, the frequency components are between 300 hertz to 3.4 kilohertz. If it is hi-fi speech, it is between 20 hertz to 20 kilohertz. Now for all these frequencies, the capacitor should act like a short circuit. So if you use few tens of microfarads here, it can act like almost like a short circuit for all the frequencies. And similarly at the output side, you have high voltage here. When this is 12 volts, this is of the order of 6 volts, and you need only an AC component by subtracting the DC. Therefore, we use another capacitor over here. And we can use another such amplifier stage here if you want more amplification, because the DC is isolated. So this is such amplifiers which use capacitive coupling are known as RC coupled amplifiers. And naturally, they cannot be used for amplifying DC signals or low frequency signals because the capacitor blocks them. So we do have DC amplifiers or very low frequency amplifiers wherein we don't use a coupling capacitor. Yes, there is a question.
So when we are applying a signal of high frequency, so it acts almost like a short circuit. So why the current doesn't pass through this?
So the question is, at high frequencies this acts like a short circuit. Why only the signal, the current passes in this direction? Please note that it's alternating current, and we have the source on this side, alternating signal. There is no alternating source on this side. It's only some load resistance. Therefore, this voltage divided by this resistance plus this impedance plus this impedance is the current, and that current flows in this direction. Hence, so conventionally we treat that the current goes inside, but for alternating signal, current going in one side has no meaning except for conventional purposes. Any other question? Any other question? Okay, so now let us look at what is the effect of this capacitance over here. Please note that the amplifier has some input impedance here. Therefore, the capacitor, on the input side, the amplifier has this kind of relationship, okay, with this kind of arrangement. And when you apply a voltage source over here, so this voltage is getting divided between this impedance and this impedance. If this is negligible, of course, this entire voltage passes to the amplifier itself. But at low frequencies, very low frequencies, so this impedance may also be as high as this voltage. And when it is equal to this voltage, this impedance, this voltage gets divided by 2 over here. And when it gets divided by 2 over here, the overall amplification drops by a factor of 2. So we expect the amplifier to exhibit low gain at low frequencies and high gain at high frequencies. So if you plot the gain of the amplifier as a function of frequency, at high frequencies it gives you full gain. At low frequencies the gain falls because of this voltage division. The input alternating signal gets divided between these two. Hence the impedance, the gain falls. Actually, gain becomes a function of frequency because of the presence of these reactive elements. If it has only terms like Ri by Rs plus Ri, it would be purely real. If it has terms like Zi by Rs plus Zi, so it becomes a function of frequency. So hence gain is a function of frequency. On the low frequency side, the gain falls like this. And what about at high frequencies? Ideally, the amplifier should work up to infinite frequencies, because these capacitances are going to act like short circuits at very high frequencies, so they do not come into picture. But unfortunately, we have some junction capacitances which come into a picture. Because of the charge storage and because the junction works on the principle of diffusion of charge carriers under voltage changes, so it exhibits some capacitance over here. And these capacitances are of the order of picofarads, and these are negligible at low frequencies, therefore we do not talk about them at low frequencies. But at high frequencies, what happens is, when you have of course a source resistance also at high frequencies, so these junction capacitances become effective and they short circuit. This is going to act like a short circuit, and so these capacitances make this Zi smaller than, or let me use it as Ri and then in parallel with this capacitance, and that is Zi. So this Zi is going to fall at high frequencies, and when this Zi falls, since the voltage gets divided between Rs and Zi, that factor in the gain, that factor which is Zi by Rs plus Zi, goes down at high frequencies. As a result, at high frequencies, the frequency response falls for the amplifier. Therefore, the amplifiers exhibit band pass characteristics. So the frequency response of an amplifier, so looks like this. Of an RC coupled amplifier, so looks like this. This is gain versus frequency. So G is no longer independent of frequency. G is going to be a function of frequency. And at the mid-band frequencies, so the gain is maximum, and at low frequencies and high frequencies, gain falls. At low frequencies, the coupling capacitance matter, and that's why the gain falls. And at high frequencies, the junction capacitances matter, and that's why the gain falls. So as you know already, so we measure the bandwidth of an amplifier by considering the 3 dB points when the gain is plotted in terms of in the dB scale. So we go for the 3 dB points, and at the 3 dB gain, or at the gain which is 3 dB below the maximum gain on the lower side, is called the lower cutoff frequency, FL. On the high frequency side, it is known as the upper cutoff frequency. And the bandwidth of the amplifier is the difference between the upper cutoff frequency and the lower cutoff frequency. This is one measure. The 3 dB bandwidth is one measure of the bandwidth of an amplifier. If you want an audio amplifier, so the FL should be less than your lower frequency, lower significant frequency in the audio signal, and FU should be greater than the upper significant frequency of your audio signal. Then this amplifier can be used for amplifying your audio signal. Similarly, for video signals, also the characteristics, the frequency response should be high for all the frequencies of interest. Otherwise, what happens? Some frequencies are amplified with some gain, and some other frequencies are amplified with smaller gain. Therefore, you don't provide equal gain for all frequency components. Unless you provide equal gain for all frequency components, so it doesn't at the output side, the signal won't be an exact replica of the input side, or the input frequency. Okay, any questions on the frequency response of an amplifier? and RC coupling. There is another very important characteristic of an amplifier, that is the linearity characteristics, or in other words, the distortion characteristics. For an amplifier, if you plot input versus output, so it should be linear. Say if the amplifier has a gain of 100, for 10 millivolts of input, the output should be 1 volt. So for 5 millivolts, output should be 0.5 volts. So for minus 10 millivolts, output should be, for minus 10 millivolts, output should be minus 1 volt. Therefore, for an exact reproduction for the input, the amplifier should have linear characteristics. If you apply a sinusoidal signal here for such a device, if you apply a sinusoidal signal, so what is this axis? This axis is VI, input voltage axis. This is VI. And I am introducing the time axis here, time. Now if I impinge this kind of voltage to the input side, when the input is here, output would be here. When the input is at this point, output would be at this point. When the input is 0, output will be 0. And so this is the amplified signal, so that can be obtained from this kind of a device as a function of time. And this is V naught scale, and this is Vi scale. I'm introducing time here and taking time here. Okay, for any input, I get the particular output, and I reproduce it at that particular time, respective times. Depending on the respective times, I reproduce that at respective times. Therefore, for any input voltage, I can find the corresponding projected output voltage, and I can find the output voltage plot. Now, this would be an exact replica of this if this is linear. If this characteristics is something like this, what happens when the input voltage rises beyond certain level? If the input voltage is like this, then what happens to the output voltage? Up to this point, well, it rises linearly up to this point. Beyond that, output is constant. Hence, you will get a distorted output like this if nonlinearity comes into picture. Now the question is, can you apply any amount of signal to the input of the amplifier? And please note that the amplifier circuits are made out of transistors. A Q point is selected, and you like to operate it in the active region, and the sources which we use typically are of the order of 10 to 12 volts. And then can such amplifiers accept signal of any voltage? So the input capacity is fixed. Therefore, there is something known as signal handling capacity. The signal handling capacity of an amplifier is fixed. In this particular application, so this is the range, amplitude range at the input side over which a signal can be applied. So when you apply a signal within this range, output would be a replica of the input. If you go beyond that, output no longer resembles the input, and output is a distorted version of the input. And this voltage range of the input voltage range for which output is almost a replica of the input, is known as the signal handling capacity. So naturally, on what does the signal handling capacity depend? On the supply you use, on the Q point you select. Okay, so let us look into this in a bit more with a bit more uh, with some more details. So here we apply a signal which is a DC plus some alternating component. In the previous example, we took the DC component as 0.7 volts at the base, and with 50 microvolts of alternating signal added to it, 50 millivolts of signal added to it, so its base to emitter potential will vary between 0.65 to 0.75, and because of this variation, the base current also has the biased base current plus some alternating base current. How does it depend? It depends on the input characteristics. If you are operating it here at 0.7 volts, this is the base current, DC base current IB. Now, when this is varied from 0.65 to 0.75, the current will vary from this current to that current. So it is equal to fixed current plus some alternating current, small ib. Because of this, we expect the collector current also to be IC plus some small ic to have, and this IC is of course beta IB plus some small IC. This IC and IB are also related by this some beta, which is not exactly equal to same beta, but around that value, which is known as beta AC. So let me write it as beta AC into IB. Now, what happens to the output side? Now at this point, so the voltage is, so V0, let me call it as V0. So V0 is VCC minus RL into IC plus I small c. And VCC minus RLIC is going to be that fixed VCE, that biased VCE, right? VCC minus RL into IC is that biased VCE. Now the output voltage is going to be, apart from the biased VCE, around the biased VCE, you have RL into IC some alternating component. Now, if the input voltage is rising beyond 0.7, say it has rised up to say 0.75, base current increases, collector current increases, and when collector current increases, so there will be a fall in the voltage. VCE would be, so if this is, say VCE is maintained at 5 volts, so it will drop. VCE would be. Okay, so let me take a numerical example. So let me take this voltage as 10 volts. And this has 5 kilo ohms. The DC biasing current is say 1 milliampere, in which case the DC biased voltage is 5 volts, and through an external resistance, I see that, say, when beta is 100, if this is 10 milliamperes, so this base current is, DC base current is 10 microamperes. Now I introduce an alternating signal here, VIT. Under biasing conditions, this is 0.7. Now with alternating signal added, the voltage will vary, base to emitter voltage will vary between 0.65 to 0.75 volts, let us say. And because of that, the base current varies between 0.65 to 0.75. Let us say the base current varies, it naturally varies around 10 microamperes. Say 5 microamperes to 15 microamperes. So base current variation is 10 microamperes plus or minus 5 microamperes due to the alternating component. Now, what would be the collector current variation? Collector current variation would be 100 times this, 1 milliampere plus or minus 0.5 milliampere is the variation. So when the input voltage rises to 0.75, input side current is going to be 10 plus 5, 15 microamperes as the base current, and the collector current is going to be 1.5 milliamperes. When the collector current is 1.5 milliamperes, what about VCE? VCE is going to be 10 minus 5 into 1.5, 10 minus 7. So it is going to be minus 2.5. 5 volts minus 2.5, it is only 2.5 volts. Now when the voltage is 0.65 volts, the base current is going to be 10 minus 5 microamperes, that is 5 microamperes. Collector current is 0.5 milliamperes, and the output will rise to plus 2.5. So for a rising input like this, the output voltage would be a falling voltage like this. So this 5 volts will go down to 2.5 when the input rises to 0.75 volts, and when the input drops to 0.65, output rises to 7.5. So please note that there is a phase inversion in the amplification, voltage amplification. It's because you are taking the output here, and the rise in the collector current reflects as a fall in the output voltage. Now, so the output voltage here, absolute output voltage, varies between 2.5 to 7.5. Now, if I further increase the amplitude on the input side, the output side amplitude can at the most go down to 0 at the output side, because below that this will be saturated, and at the most it can go up to 10 volts. With 0 current it can go up to 10 volts. It cannot go beyond that. Hence, the output voltage swing is fixed by on the lower side it is fixed by this VCE, a biased VCE, and on the upper side it is fixed by, so the voltage drop across RC under biasing conditions on the output side. And similarly on the input side also they are limited. So if this voltage is too high, you will have distortion here occurring here, and if this input voltage is too low, the input current may be 0 and base current may be 0, therefore output collector current would be 0, and the total voltage will be fixed at 10 volts itself. So output will be distorted at 10 volts. So you will have, if the voltage is further increased like this, you will have distorted output. And naturally these are fixed by the biasing voltages and the supply voltage and so on. Okay. Next we shall discuss about the transistor modeling, the other issue involved in the in obtaining the amplifier model from a transistor circuit.